Now we're thinking about standing waves. And remember what you read in the text and saw in those videos. A standing wave is what you get when two traveling waves moving in opposite directions combine. And the difference between a traveling wave and a standing wave is that in a traveling wave you actually see the wave shape traveling. In a standing wave you don't. In a standing wave all you see is the individual bits, the individual masses that are in the path of the wave, or the individual bits of string, to use our usual wave model, the individual bits just oscillating because waves are passing through those points. And you see how all that works, how the two traveling waves combine to produce the standing wave. In figure 16.6 in chapter 16. Look at that figure very carefully, study it very carefully to see how all this happens, how the waves combine to give you a standing wave, and what the standing wave looks like. Let's just go into a little bit of detail on what a standing wave would look like if you were to slow it down a lot. Here's 4 different snapshots of a standing wave at 4 different times. Time 1, I'm calling the time when every oscillating point on the string is at its maximum distance away from equilibrium. If the string is undisturbed, if there's no wave pushing and pulling the little bits of string, the string would just look like this, horizontal. This is the equilibrium position for every point on the string. And when the bits of string are oscillating, they're all feeling a restoring force that is always pulling them towards equilibrium. So all these points are the locations, or the displacements of little bits of string at one moment, in particular the moment when they're at the maximum distance away from equilibrium. So of course, since they're not getting any farther away from equilibrium than that, at that point they must have stopped moving away from equilibrium. Speed is 0 at that moment. And then, as time goes by, as you go from time 1 to time 2, every point is moving towards equilibrium. So, for example, this point will have moved from here to here, and then this little bit of string will have moved from here to here, and this bit of string would have moved from here to there. And then at time 3, very shortly after that, every oscillating bit has continued to move closer back towards equilibrium. So this little point is now here, and this little bit of string is here, and this little bit of string is right there. Everything moving closer and closer to equilibrium. And as we know from oscillations, as an oscillating mass gets pulled closer and closer to equilibrium, it speeds up. So this point, which had 0 velocity when it was at its greatest distance away from equilibrium, has been speeding up. It's got a higher speed at time 2, an even higher speed at time 3, and an even higher speed at time 4. At time 4, every bit of string has returned to its equilibrium position. Every bit of string has now gone through 1/4 of a cycle. And that is, this point is now moved all the way from here to here. This point has moved a shorter distance from here to here. This point has moved from here to here. And then continuing through the next quarter cycle, this point, it's at equilibrium at time 4, every point is at equilibrium at time 4. So the x point is there, and then the 0 points are at here, or the dot points are here and here. And then time 5, a little bit after time 5, every point has now started to move away from equilibrium in the opposite direction, on the opposite side of equilibrium from where it was during the first quarter cycle. Right? This is just what any oscillating object does when it oscillates. And any little bit of mass that gets in the path of a wave will oscillate. So at time 5, every piece of string is now at these displacements. And so these bits of string are here and here, and this bit of string is here. And then at time 6, everything has continued to move farther and farther away from equilibrium, so all the little bits of string are at these points. This piece is now here, this piece of string is here, and then finally, at time 7, every little bit of string is now, once again, at its maximum displacement away from equilibrium, just on the other side of equilibrium from where it was a half cycle earlier. So this bit of string is here, this bit of string is here, this bit of string is now here. And again, being at the maximum distance away from equilibrium, it's not getting any farther away, so it means it must have stopped at that point. Stopped, and then so it can turn around and immediately start moving back towards equilibrium after that time. So what do we see? Just take a look at the dot pieces of the string. In one half cycle, the dot pieces will have moved like that. And then in the next half cycle, they'll move like that, so that at the end of one full cycle, they'll be right back to where they started. The way we usually illustrate a standing wave is a picture that has 2 snapshots, like this. One snapshot at one time, let's say this is, let's call that time 0, and then another snapshot half a cycle later. So if every piece of the string is at those locations at time 0, and again, let's say that starting time is a moment when everything is at its maximum displacement away from equilibrium, then half a cycle later, right, this piece will have moved from here to here, and the piece that started out here will have moved from here to here, and the piece that started out here will have moved from here down to here. And again, this curve the snapshot after half a period has happened. So every piece has gone through half a cycle. That means everything has gone from its maximum displacement on one side to its maximum displacement away from equilibrium on the other side. And what these 2 snapshots together represent is sort of the region within which every oscillating bit of string oscillates. That is, the point that would be sitting right here, if nothing were happening to the string, oscillates between here and here, and this point on the string which would sit here if there were no waves on the string, would oscillate between here and here. And in a full cycle would oscillate from here to here, then back to here, just as this point in a full cycle would oscillate from here to here and then back to there. Okay, so in other words, this bit of string oscillates from here to here. There's its maximum distance away from equilibrium. In other words, this is the amplitude of oscillation for this piece of string. And this is the maximum distance away from equilibrium for this piece of string. So this is the amplitude. And then imagine a little piece of string right here. It'll oscillate at time 0. That little piece of string is right here, and half a cycle later it's right here. So it oscillates from there to there and back in one cycle. So there's the maximum distance away from equilibrium. There's the amplitude for that little bit of string. So one feature of the standing wave that makes it look different from the traveling wave is that every piece along the path of the wave has a different amplitude. Some really big amplitudes, some small amplitudes, and every once in a while a point with 0 amplitude, points that don't oscillate at all. And remember from the text, we call those nodes, and we call the points with the maximum possible amplitudes antinodes, just the opposite of nodes. One important fact about nodes and standing waves is that whenever you have those two traveling waves causing a standing wave, remember those two traveling waves have the same wavelength and frequency, and they're both moving along the same medium, so they have the same speed. The only difference between those two traveling waves is that they're pointing in opposite directions. What's really going on is that one wave is a reflection of the other wave. And when they produce a standing wave, the distance between nodes is always equal to half wavelength, half the wavelength of those traveling waves that combined to produce the standing wave. Okay, so let's just look at that in a little bit more depth. It turns out that only particular wavelengths and frequencies will produce standing waves. A traveling wave of any wavelength or frequency could move along this string, but only certain particular wavelengths and frequencies will produce standing waves. So, what are those magic frequencies and wavelengths? There's an easy way to figure that out, because the facts that we start with are pretty straightforward. The two ends of the string are always tied down, fixed. I can think of a guitar string. You pluck the guitar string and it vibrates, but the ends of the string don't vibrate. They're fixed in place. So, in other words, the two ends of the string are nodes, which means here's the the simplest kind of standing wave that you could have on in any system like this where the two ends have to be nodes is one like this, where there's the snapshot at one time, and there's the snapshot a half cycle later. Every point on every vibrating point was at its maximum displacement on away from equilibrium on one side, and then half cycle later it's at its maximum displacement away from equilibrium on the other side. This is the simplest standing wave in the sense that it has the fewest number of nodes. You have to have nodes at the two ends, so the minimum number of nodes is going to be 2, and this standing wave has the minimum number of nodes. This corresponds to a particular frequency and a particular wavelength, because remember, distance between nodes is half a wavelength. So if we take, let's call L the whole distance of the string, then in this case L is just equal to half a wavelength. One step, just between one node and the next, that's the whole string length. Or to put it another way, the wavelength of the waves of the traveling waves that combined to produce this standing wave have a wavelength equal to twice the string length. Now, use our basic equation for traveling waves that relates wave speed to frequency and wavelength. There's the rule. So what kind of frequency would this wavelength correspond to? Well, frequency for any traveling wave is just wave speed over wavelength. So in this case, the wavelength is 2 times string length. So we have speed over twice string length. Let's keep that result in mind. So that was so this is the frequency and the wavelength that will give us the simplest standing wave. The next most simple standing wave, the second most simple standing wave, would then have one more node than this, 3 instead of 2. And what would that look like? Well, let's draw the double snapshot picture for that one. In that case, at one moment in time when everything is at its maximum displacement away from equilibrium, the string would look like that. And then half a cycle later, everything would be at its maximum displacement away from equilibrium on the other side. And so the string would look like that. And in that half a cycle, all points will have moved from their maximum distance away from equilibrium that was like this to maximum distance away from equilibrium that was like this. And let's go through the same procedure here as we did here. Here, node to node, that's half a wavelength. Node to node, that's a second half wavelength. So the entire string length is equal to 2 half wavelengths. I won't cancel out those 2's for reasons that we'll see in just a minute. So what that means is that we can write, in this case, the wavelength of the string is just 2L over 2, and then find the frequency by using the basic traveling wave equation. Frequency is wave speed over wavelength, In this case, wavelength is 2L over 2. So we have speed over wavelength, which is 2L over 2, or 2L over 2. So that's the second wavelength and frequency that would be just right to give you a standing wave. That, and because I kept those twos, then it's easy to see how those two frequencies relate to each other. This frequency is twice as big as this frequency. Oh, sorry. 2V over 2L. This is just plain V over 2L, and this is V over 2L times 2. So we usually would refer to this frequency, this lower frequency, as 1, and this one is 2, meaning that this frequency is twice as fast as this one. Then we'll do this one more time and we'll see a pattern. This standing wave had 3 nodes, the 2 nodes at the end that always have to be there, plus 1 in between. Then the next standing wave would have a grand total of 4 nodes instead of the 3 that these have, 2 at the ends and 2 in between. So it would look something like this. At one moment in time, when everything is at its maximum displacement away from equilibrium, a snapshot would look like this. And then half a cycle later, a snapshot would look like this, when everything has gone through half a cycle and now is at its maximum distance away from equilibrium, but on the opposite side of equilibrium. Going from this shape to this shape. Now, do the same thing. Node to node, that's half a wavelength. Node to node, a second half wavelength. Node to node, a third half wavelength. So in the entire string length, 3 half wavelengths fit onto that string length, which means that the wavelength itself is just 2L over 3. So the frequency associated with that wavelength is wave speed over wavelength, which is wave speed over this wavelength, 2L over 3. And then let's write that along with our previous 2 results. Frequency is 3 wave speed over 2L. Well, speed over 2L, there's the lowest frequency, and this frequency is 3 times bigger than that, so we'll call it F3. And now you see the pattern. You've got a lowest possible frequency at which you could vibrate the string to get a standing wave. You would also get a standing wave if you vibrated it 2 times as fast. You would also get a standing wave if you vibrated it 3 times as fast, and so on. So the frequencies that will produce standing waves in this particular system for the string that's tied down at both ends, there'll be different rules for standing waves for different kinds of systems, but this is the simplest one to think about. The rule is simply this. There's a whole range of possible frequencies, and we'll identify each of those possible frequencies with with a subscript here, M, which is just some positive integer, 1, 2, 3 for example, and all of those possible frequencies are just some integer multiple of the lowest possible frequency. And m is any positive integer. In other words, you can vibrate a string at any frequency you like, and that just grab some piece of the string and shake it at any frequency. That will then become the source of a traveling wave. Traveling wave moves to the end of the string and gets reflected. So now you've got that reflected wave, and you still have the original wave moving away from the source over here. Now you've got the two waves, and they combine according to the principle of superposition. That happens no matter what frequency you shake the string at. But if you were to shake the string at these frequencies, you get the standing waves. The significant part there is that the standing waves will have bigger amplitudes than any situation where you shake the string at a non-standing wave frequency. You'll get smaller amplitudes. Well, bigger amplitudes sometimes, smaller amplitudes for other frequencies. We've seen that before. Way back in chapter 14, that's what we call resonance. Remember what that means. There are certain frequencies at which a system most easily vibrates. Certain frequencies at which a system likes to vibrate, if you want to put it that way. And those frequencies will be frequencies at which you get the biggest amplitudes. If the frequency at which you shake the system, if that's one of the preferred frequencies of the system, the oscillations that you get will have big amplitudes. If you shake the system at a frequency that's very different from the preferred frequencies, you get small, sometimes tiny, insignificant amplitudes. That'll become significant when we think about standing wave, in particular about standing waves and how they produce sounds, musical sounds especially. That's what we'll think about next time. Here we're just looking at the basic principles of standing waves. Standing waves, being resonances, have the biggest amplitudes, which kind of hints that in many ways they'll be the most important kinds of oscillations that a system could have. So one example of thinking about standing waves is take a look at these three standing waves. And let's say that this is just the usual double snapshot for a standing wave on a string, and this particular string is 30 centimeters long. And at one moment in time, when every oscillating bit of string was at its maximum displacement away from equilibrium, the string would look like this. And then half a cycle later, when everything was at its maximum displacement on the other side of equilibrium, the string would look like this. So those two snapshots show the space within which every point on the string will oscillate. the next standing wave is like this. And the length of this string we'll call 35 centimeters. String A, string B, and then string C. And then that's the longest string of all. We'll say it's 40 centimeters. We can rank we can rank those strings in terms of wavelength of the traveling waves that produced these standing waves. And we just do that just by using that principle that I mentioned, that principle that is mentioned in the book, half wavelength between nodes. So for standing wave A, on that entire string length, which is 30 centimeters, we have 1, 2, 3, 4, 5, 6 half wavelengths. 6 half wavelengths fit onto the entire 30 centimeters of the string. So this is the same as 3 times wavelength. 3 times wavelength is 30 centimeters, so the wavelength itself is 10 centimeters. And for B, just do the same thinking. The entire string length of 35 centimeters has 1, 2, 3, 4, 5 half wavelengths. Node to node, first node to node, second node to node, third node to node, fourth and fifth node to node. So the entire 35 centimeters equals 5 half wavelengths. So let's do that algebra here. 7, multiply both sides by 2, and then divide by 5. So 70 centimeters divided by 5 is equal to 1 wavelength. That means 1 wavelength will be 14 centimeters. And then what kind of wavelength for standing wave C? How many do the same thing, ask the same question? How many half wavelengths fit on that string? 1, 2, 3, 4, 5, 6, 7. 7 half wavelengths fit on the entire string length. So the entire string length of 40 centimeters is equal to 7 half wavelengths, or 80 centimeters divided by 7 is the wavelength. So that would come out to about 11.4 centimeters for the wavelength there. And then the ranking of those 3 different standing waves, ranking in terms of their wavelengths, B has the longest wavelength. And then C has the next longest, about 11, and then A has the shortest, 10 centimeters. Okay, that's just an initial example of how to think about standing waves. In class, we'll practice some more with these basic ideas and then start to think about what standing waves actually do in real-world situations, especially in the production of sound and the production of the human voice and production of musical sounds.